So we'll present you today History's project, over the overall project. You've seen 2 talks on 3 work packages of the project before. And also focus on one topic, which is the ranking of possible storage sites in Europe. So as said, I will introduce the project, and about ranking, I will have to develop that a little bit more, starting by asking why should we store hydrogen, because I cannot rank if I don't know why, and then focus on the cost and try to explain how do we know what is the cheapest storage technology, and then I will show you our proposed ranking scale, which is an ongoing work. So the project, it's a European-funded project. So it's basically in the frame of the ambition of the EU of being climate neutral by 2050. So this has set the scope, and for that, the EU was funding a research project focus on pure hydrogen storage in porous media. So this was set by the call for proposals, and we answered by proposing works in 2 directions, the 2 pillars of History's. First pillar is that we need some additional technical developments on some topics, because pure hydrogen has never been done in porous media to date. This is first pillar of History's. Second one is that this is an infrastructure business, developing underground storages. It takes decades, and developing surface pipelines that are connected to it, it's the same. So it takes decades, so we need to provide insights to decision makers, to make them, to give them some required inputs to make their decision and to plan these infrastructures in advance. To work on this, we gathered a team of companies or research institutes from 17 European countries. So it's coordinated by Geostock. I'm the coordinator. CO2 GeoNet is the second biggest partner, but CO2 GeoNet in the consortium is represented by 17 research institutes or geological survey. So as said by Jan earlier, we are very happy to have CO2 GeoNet in this project. As said by Kerry as well, there is no European geological survey, and CO2 GeoNet is playing this role and is playing that role very well. And I thank you, and I know that this budget divided by 17 is quite limited, so I thank this effort to participate to the project. We also have an advisory board in this project that is quite large. I will explain why. It's 13 companies. The biggest natural gas storage operators in porous media are there. And all these working teams or advising teams are there for this work program. And also there is a timeline at the top. So here we are in San Savolo. We are a little bit after half of the project. So we find again the 2 pillars of the project, and I will try to explain each of the works that we do. So I will go very quickly for those that have already been presented. So as presented by Kerry, CO2 GeoNet has worked and developed and adapted the knowledge gathered on CO2 geological storage to build this database of porous media traps for hydrogen underground storage. Jan has presented how it's used for estimating the capacity of hydrogen storage into them. Joe has presented the extensive microbiological program that is done in the project. So this is why we have so many advisory board members, because many of them, they are providing us with brine sample from their gas storage sites. Not in the idea of doing an analysis for them, but in the idea that we gather brine samples and their microbiological fauna from a number of sites with a number of different conditions, and that we will then be able to draw results that can be representative or can be used in future developments in other sites. We work at University of Leoben on qualification of steel materials for hydrogen in work package 4. So this is the technology development, and here it's focused on porous media. And then on the right part of the figure, we've got our techno-economic feasibility studies. And here, to do not bias the comparison, we consider both porous media storage and salt cavern storage. So we have work package, and I will detail that later, work package 5 which is done by LBST, a German consultant. They have built an energy system, a model of the energy system of Europe, and at each time step they match the energy supply and demand with the introduction of underground hydrogen storage as a buffer. And so it leads it enables us to have an estimation of the optimal storage in each of the 27 European Union member states, plus UK. We also work on, and it's FHA that works on Work Package 6. They have done a review of the readiness of European regulation for having underground hydrogen storage. And so they also had a lot of support by CO2 Geonet members participating to the project and by advisory board members in this task. And and we have a work package 7 that is building a cost model and using it to rank site candidates that could be potential hydrogen storages. So this will be the main focus today. So we'll start by asking, why should we store hydrogen? What are the drivers? So for CO2, you're familiar with that. We store that for not having it contribute to greenhouse effects. As Kerry said, again, CO2, hydrogen, we want it back. CO2, we don't. Yes. We need, I put 1,000 years here, but it's more 10,000 years, I think, that we find. We need it away from the atmosphere for at least this duration. And we don't want to produce it. There is no question of deliverability. For others, there is a big question of deliverability. What flow rate are you able to withdraw? So if we look at why do we store oil on the ground, it started in Canada in the 40s, in the middle of World War II. And in Europe, it developed after the oil crisis 50 years ago, when oil exporting countries stopped exporting. So it's mostly, it's called usually strategic storage, and it's mostly geopolitical reasons, and it's supposed to last many years, let's say, at least 3 years. That's what we see in storages in operation. Natural gas, initially it's there to cope for the high seasonality in demand. A few years ago, with the development of liquefied natural gas, it also was used for trading reasons, to grab a cheap carrier, etc. And now or tomorrow, we will also have geopolitical reasons for storing natural gas. And the storage pattern is mostly seasonal. It's what is existing today, at least. Here you have the picture of the pressure at the wellhead of one storage site in France, and you see it's a very seasonal pattern, very regular, and it's basically 4 months of injection, 3 months of standby, and 2 months of withdrawal, or something like that. And we also have a lot of storages of LPG, of hydrogen as a feedstock of petrochemical industry. So here is an example of one salt cavern storing hydrogen in Texas. And you see, you see it started operation in 2015, this one. It's been idle and full for 2-3 years, totally full. And then it was totally emptied over a few months to be able to answer the standby or the maintenance on a plant, and it was very profitable for the company. So now we're looking at green hydrogen. And green hydrogen, we don't really know, it's not obvious at least, why should we store it? Is that for power to power? Is that for power to mobility, power to gas, power to industry? The only thing we really know is that it's power at the beginning, because for green hydrogen it has to be green power and electrolysis to produce it. So we have a variability on the renewable energy sources that we have to cope with. Maybe also variabilities on the consumption side, and we can imagine many cycles. But at some point, intuition is not enough, and that's why we have included this work by LBST in the project. So they've defined properly 4 scenarios. All of that is on our website. 4 scenarios: imports or not, salt caverns only or both technologies. They have, as said, modeled the European energy system at each time step, and they have first estimated the optimal storage capacity per country, then also estimated the optimal deliverability capacity per country, and also it gives us typical cycles. So this is an example of their results in 2050 for France for 2 scenarios. And here, in this case, we find an essentially seasonal cycle. And it's important to have the shape of the cycle, because the slope of the injection and withdrawal that you see here, it is defining, the power of the compressor and the power that you need on your site. And it is impacting a lot the cost of your facility. So now we have our cycles. Now for a given cycle, we have to look at what is the cheapest technology. So here I will try to go a little bit away from histories and try to go 3 years back. And I will reuse 3 slides I presented at the European Workshop on Underground Energy Storage in Paris in 2019. So I think many of you, or several of you, were there. Maybe it was right before COVID, so maybe it was the last time you met in person. And so maybe it will be redundant for you, but also it's not the easiest slide to explain. So it may be. I hope it will still be useful. So I will focus on the case, a hypothetical case of power to hydrogen to power, to simplify things. So you probably know that we don't know how to store electricity. It's an energy we cannot store like this. We have to transform it to chemical energy if we produce hydrogen, to electrochemical energy if we store it in batteries. But electricity itself, it cannot be stored. So we can see this kind of storage. The components of this storage, we can put them in 2 categories. So there are the equipments. We have to transform this electricity into something we can store. And we have to transform it twice, actually. We have to transform electricity energy into an energy we can store, and then to transform back this stored energy into electricity. So there are equipments that are associated to the transformation capacity, and they are associated to the power of your plant, and there are equipments that are associated to the capacity of the facility. Here, typically, it would be a porous storage or salt caverns. And now, if we try to look at what is the best solution, what is the best storage technology, well, let's imagine we've got 2 technologies. So one is technology 1 with a quite cheap transformation equipment and a quite expensive storage equipment, and it's the opposite for the second one. And then we've got 2 cycles that we want to meet. Same power demand, same total injection duration, half the year for each, but either 12 hours and 12 hours, or either 6 months and 6 months. So totally different storage capacity required. So if we just multiply the power times euro per kilowatt and the energy times euro per kilowatt hour, we find totally different numbers and not the same winner. So if we've got short cycles, it's not a big problem to have expensive storage equipment. If we go on long cycles, we need cheap storage equipment. So this is an simplified approach. Reality, again, is more complex, of course. But we've got a useful tool, which is called levelized cost of storage. Let's say it's the break-even selling price of the energy storage service. And if you know your cost, if you've got your cycle defined, you can compute this levelized cost of storage. And this has been done on the right by IEA. You don't see that here, but in 2019, for instance. And you see that for short cycle, technologies are, like batteries are clear winners. But if you want to store 100 times more longer, then for batteries you need 100 times more batteries, and you have got 100 times higher capex. If you would have power to hydrogen to power, you just have to have more salt cavern or porous media, which is the cheap part of the equipment. You don't have to multiply your electrolyzers or fuel cells. So I hope that was clear enough, and it is just to say that the cost structure matters. And this is why we needed to define the capex, the fixed opex, the variable opex of our underground storages. And also we face difficulties that in this underground world, it's always case specific. So we defined conceptual designs properly, and we built project-based cost estimates that enable us to have a cost. We know what it is, the boundaries of this cost. We have a parametric model, and we can distinguish cost of storage and cost of withdrawal. So we find back the idea I was trying to explain before, and also it's hydrogen specific. So I will go quickly just to say that it is available on our website. This is as a design parameters. Let's say it was reasonable design parameters for the salt caverns. For porous media, we based ourselves on analogs of natural gas storages, of European natural gas storages. And we've got results from that. First, we've got results of cost for these conceptual designs. So we've got subsurface costs. So we find it's not surprising that it's higher for salt caverns because you have to develop the cavern. The porous media you don't have. We find that surface costs are higher for porous media. Not surprising either. At the end, we find actually almost the same cost for our typical designs, capex cost. And this is the cost we've used in the energy model I've presented before. We have another thing for this result from this work, which is this parametric cost model. So basically, we've got a cost that is well defined and depends on a number of parameters. And these parameters are those we can find in what was developed by CO2 GeoNet in Work Package 1, like depth of the storage. And also by the Work Package 2 with the capacity, etc. So we can apply this cost model to the data we had on 700 traps. So my last slide, oh no, I've got two. So what do we rank? So we rank the two options that are more or less in competition for infrastructure storage of hydrogen in Europe, porous media and salt caverns. So for porous traps, we have this database from Work Package 1. So as said, the capacity is based on what is identified for aquifers and what is public for depleted fields. So it's rather a minimum. And for salt caverns, we are using SMRI compilation of salt deposits and its analysis by a thesis by Weber. That is giving us a maximum capacity. It's basically putting salt caverns everywhere on the salt deposits, so it's rather a upper boundary. It's a little bit like for aquifers, you will assume there are traps everywhere in your sedimentary basin. But for salt caverns, it's closer to the reality. And then my last slide. So we are proposing to rank these sites on 4 scales, actually. So one is using these cycle patterns, this parametric cost model, and this database of traps from high storage work package 1 and 2, and database of salt deposits from SMRI to estimate a levelized cost of storage for relevant storage cycle for both porous media and salt caverns. Another is capacity. This is only done for porous media. This is what Jan has presented earlier. And the third one is based on the work that has been presented by Dieu. And it will rank sites depending on the temperature, salinity, and risk of having sulfates and carbonates on a simplified scale, and to assess whether or not it's favorable regarding the risk of microbiological activity. And last mark will be based on remaining parameters that can be found on work package 1, like presence or not of faults, of a number of abandoned wells, etc. So this is the work we are pursuing today. And so this work is an introduction to the work of high stories. It's a big project. It's hard to summarize that in 20 minutes, even in 3 presentations. The final conclusions are not there yet. They will come with the end of the project next year. Also, would like to inform everyone that there will be a final conference probably in June 2023. So you can let me know if you're interested to attend. And also, nearly all our results will be public and will be published on www.highstories.eu. So you can check this website. So we thank the EU for funding us and all the project consortium for this work. Thank you.